Hey, and welcome back to part 4 of the Kerberos Deep Dive series. I'm Alex, and in this part we start looking a bit more closer into the delegation features available in Kerberos. Specifically, in this part we cover the unconstrained delegation. Before we start with the actual topic, a quick note, as within the other videos, on the usage of Wireshark. We'll be using Wireshark to inspect Kerberos traffic at certain points, and since Kerberos traffic is at least partially encrypted, this will make it much more difficult to actually analyze what's going on. So in our lab environments and in the videos I'm going to show, we have configured Kerberos key material within Wireshark, so Wireshark will be able to decrypt all Kerberos traffic. Now, whenever you see Wireshark and it contains a section highlighted in blue, as shown here on the screen, this part would normally be encrypted, and as with the provided key material, Wireshark is able to decrypt it so we can look at the actual contents. If you want to learn more about how this can be done, go back to part 1 of this video series. Now, let's start with a few basics on what delegation actually is in Kerberos. Essentially, the delegation feature is a standard built-in feature of Kerberos, at least in the Microsoft version, MS Kyle, and it basically allows a user or a service to act on behalf of a user that connects to it when it then talks to other services in the backend. So essentially, it's user impersonation in Kerberos terms. We've got a quick sample scenario here. Imagine we have on the left side our user Alice. We then have an application, for example, a web application, and we might have a file share in the backend. And now when Alice authenticates to the web application, what we want to achieve with Kerberos delegation is that the application can then act as the specific user against the backend resource. For example, a file share. So if the application wants to access file shares, she will actually do so, or it will actually do so in the name of Alice. So the permissions applied to Alice and the file share will be evaluated. This allows us to specifically grant permissions on the files to the respective user, and we will not have to configure a almighty service account that has access to all the files on the file share on the web application. So those are the benefits, potential benefits of a delegation scenario. Now, in the Windows version of Kerberos, there are 3 main delegation mechanisms. In this video, we're going to be talking about the first, which is unconstrained delegation. The unconstrained delegation is the oldest one. It has been introduced with the Windows 2000, and in its form, it's the most simple delegation mechanism. Essentially, if you grant the delegation unconstrained delegation to a system, that means this system can then impersonate users against any other services within your domain. Compared to that, in Windows Server 2003, constrained delegation was introduced, and as the name says, it adds certain restrictions and constraints to the impersonation or delegation process, specifically against which targets of services you can perform impersonation or delegation. So if you grant a system constrained delegation rights, that means this system can still impersonate any user, but only again against a specific group of services that you can specify. And lastly, with Windows Server 2012, there was the introduction of resource-based constrained delegation, or RBCD for short, which essentially just reverses the way delegation is controlled or configured. So instead of a service being allowed to delegate to a certain set of backend systems, the backend system specifies which services are allowed to delegate against it. The mechanism underneath it is essentially the same, but the way the configuration is applied is essentially reversed and centered on the resource. That's why it's called a resource-based constrained delegation. Now, there are certain restrictions that apply to delegation mechanism. The first one is a mechanism for that is called sensitive users. So you might not want to delegation to occur for all your accounts within your domain, especially high privileged user accounts. And this you can achieve by, or you can prevent delegation of those accounts by flagging those as sensitive. So it's just a setting that you can configure within your, for example, Active Directory users and computer configuration panel, and tick this box on any given account to mark it as sensitive. For those accounts, Kerberos delegation does not work anymore, so it will result in an error. And it is obviously recommended to configure this for your high privileged user accounts, so it's less likely that they are abused by an attacker. If you're familiar with Pinkastle, this will also be pointed out to you when you run a domain health check, so you will be able to see which users are configured as sensitive users and if you've missed some high privileged user accounts. One important thing to notice is that this setting is not active by default. So if you install a new domain, configure new users, none of them will actually be flagged as sensitive. Another restriction that also applies to Kerberos delegation is the so-called protected users group. This is a built-in group in any Windows Active Directory environment, and it is designed to restrict or apply certain restrictions regarding credential exposure to all its members. The restrictions that are applied are actually not configurable, so they apply to all the users within the group in the same manner, and you cannot adjust them in any means. Specifically, what you have to keep in mind that this has to be configured only for actual user accounts, so not for services or machine accounts, since those restrictions would break certain functionalities and mechanisms which are normally desirable for those kind of accounts. If we look at the mechanisms that are actually applied, essentially it's preventing caching of credentials, be that plain text passwords or other authentication material like anti-hashes and so on in the cache of a system. It will also disable NTLM authentication. So this protocol, the NTLM protocol, cannot be used anymore to authenticate. Weak ciphers will automatically be disabled, so no DES or RC4 for Kerberos tickets, for example. And among other things, it will also prevent Kerberos delegation. Lastly, the authentication material is also more time restricted, so the window of abuse is shorter. And again, as with the sensitive users, this group is empty by default, so there are no members of it. And just one thing to keep in mind at the end, it's always a good idea to not put all your domain admins and other high privileged user accounts in this group and keep one emergency account, a break glass account, out of the group in case something goes wrong. For example, if Kerberos is not available in your environment, you would not be able to log in anymore if all your accounts are in this group. One more thing regarding delegation that is maybe not apparent in the beginning is that delegation is essentially transparent to the user that is being delegated. So the user that connects to a system and then the system is configured for delegation, the user does not actually have any say about whether delegation will occur or not, then they don't even see whether this is done. So the system that is configured for delegation is essentially the one that decides whether it wants to take action on that and perform delegation or not. And the user, even first, as I mentioned before, has no say in it, and it is also not technically possible for a user to see if delegation has occurred directly. Now, before we look into how unconstrained delegation actually works, a quick refresher on the Kerberos basic authentication flow. We have learned already that in Kerberos, a user first has to acquire a so-called ticket granting ticket from the KDC, and this ticket simply proves that the user is who they say they are. With the ticket granting ticket, a user can then in a next step request so-called service tickets to prove their identity to various target services. And they request a service ticket for each new service they want to connect to. So if we look at that in a diagram, the user will first request a ticket granting ticket. if everything is in order, so the user is correctly authenticated, the KDC, or specifically the authentication server part of the KDC, issues the ticket granting ticket. And with this TGT, the user can then request service tickets for any service within the domain that has a SPN, so a service principal name configured. In our example, could be CIFS, so a file share running on foo.local over here. The ticket granting server part of the KDC will then issue a service ticket. And again, here it's important to know that there's no authorization decision taken at this point. The ticket granting server simply issues a service ticket as requested, and eventually when the user then connects to the target service and presents the service ticket, then an authorization decision is taken by the actual resource. So with that, let's look at how unconstrained delegation actually works under the hood. With unconstrained delegation, if a user first connects to a service or a system that is configured for unconstrained delegation, the service then receives a copy of the user's TGT. So the TGT of the user is essentially duplicated, and the TGT is then forwarded to whatever service is configured for unconstrained delegation. With the TGT, this service can then essentially request service tickets on behalf of the user. So it can imitate the behavior of the user, it can present the user's TGT to the KDC and request service tickets for further services in the backend, and therefore then act on behalf of the user against those services. If we look at that schematically, we start with the first service ticket request. So the user has already acquired a service ticket or a ticket granting ticket, and will then make a first request for a service ticket for a specific resource. In our case, that could be HTTP on web.local, so a web application. And as you can see in our example, web.local is configured for unconstrained delegation. What the ticket granting server will do is, upon the request for the service ticket, it will check if the target has any delegation rights. So in our case, that will be unconstrained delegation. And if this is the case, it will indicate that in the response. So it will return the service ticket along with a flag called OKSDelegate, which instructs the client or lets the client know that it requested the service ticket for a target that is configured for unconstrained delegation. Next, what happens is that the client automatically, without any input from the user, will request a copy of its TGT. So it will again go back to the ticket granting server, present its original TGT, and as a result, get back a second version of it. So essentially a copy. The second version of the copy of the TGT is then simply glued on to the request that is made to the actual server. So when the user then accesses web local, it will first present its service ticket, which still is evaluated so the service can identify the user and make an authorization decision. And with the same request, it will also forward the copy that it has received. And then the web.local is now in possession of the user's TGT. With this copy, the web.local service can simply then extract it, go back to the ticket granting server, present the service ticket, and now essentially do this exact same thing as Alice has done in the first step, request a service ticket for any given resource, for example, for a SQL service running on db.local. The ticket granting server will still evaluate the TGT, the same rules applied as in this step. And if everything is okay, a service ticket for Alice is returned. And with this service ticket, the web.local system can then access further resources. And this looks then essentially the same as if Alice had done this step. So this is how unconstrained delegation is implemented from a logical or process view. Now, if you want to configure unconstrained delegation, this has to be done on the respective domain object. So that is either a user or a machine account. And configuring unconstrained delegation requires domain admin rights, or specifically a privilege called SE-enabled delegation, which is typically only granted to domain admins. in the Active Directory and user and computer configuration panel, this looks like that. So if you go to any account, for example here the WS1 computer account, and then go to the delegation properties, you can set this setting called trust this computer for delegation to any service, and this essentially will enable unconstrained delegation for this account, or grant this account unconstrained delegation permissions. We can quickly look at this in PowerShell as well to query this information. I'm on the domain controller currently, or you can do that on any other machine that has the Active Directory PowerShell module installed. And with that, we can simply issue with the get AD computer if we want to check computer accounts, and filter for any system with this trusted for delegation filter. Now we can see we have two systems. We have the domain controller and we have the WS1 machine. Now a note on the domain controller. Domain controllers are by default always configured for unconstrained delegation. So they will always show up. This is also something you cannot disable. This is essentially required for the domain to function properly. So domain controllers will always show up if you issue this query. What we can do to get a more precise picture on which systems have this enabled specifically, besides the domain controller, we can add another filter for, in our case, just the domain computers. So this will eliminate domain controllers. And now we can see that only WS1 is returned as a result. If we want to do the same thing for users, we can essentially repeat the command with simply the get AD user commandlet. Now the same filter is applied. Here we don't need to filter out domain admins or something like that because they don't have this right configured. And as you can see in our case currently there's no user configured for that, and we can just for demonstrational purposes quickly enable this feature. So we go to one of our accounts, IAS service account, and then in the delegation tab we enable this unconstrained delegation option. And if we now repeat our query from before, we can see that the IAS service account now shows up to be configured for unconstrained delegation. Now, if you apply unconstrained delegation, there are also certain security risks that come along with it that you need to be aware of. The form of a delegation that we are looking at is by definition and by its name unconstrained. What does it mean? The service can impersonate the user against any other services within your domain. That's where the unconstrained part of the name comes from. This makes those services obviously a very high value target for attackers, since if they are able to compromise these services, they can then perform the delegation against any other service within the domain and essentially impersonate arbitrary users against all other services, which then eventually leads to privilege escalation. Of course, the impact of this always depends on the delegated account. So if you delegate a regular user that doesn't have any elevated privileges on any other services, you don't really gain anything from it. But if you are, for example, able to delegate a domain admin, if it's not sensitive and not in the protected users group, you obviously will be able to escalate your privileges on any other service that you can connect to. So in a sample scenario, if we have again Alice connecting to our web server, and then the regular scenario, the intended scenario will be that the web server can impersonate or act as Alice against the database. However, since this is unconstrained delegation, if the web server is compromised by an attacker, meaning the attacker gains full control over the system, in this scenario now the attacker will be able to abuse this delegation right and act as Alice against any other system, for example web applications, file shares, databases, and so on, within the domain that are part of the Kerberos authentication realm. Now, if Alice is a domain admin, again, as I said before, this would have grave consequences. Now, how can unconstrained delegation actually be abused? So what are the steps necessary from an attacker's point of view? What we want to achieve essentially as an attacker is to steal and abuse the ticket granting tickets, the copies of the ticket granting tickets of other users when they connect to the system that is configured for unconstrained delegation. And with the TGTs, we will then be able to request service tickets for any other resource in the domain, because this is the way unconstrained delegation is implemented. So what we need to do as an attacker is we need to get control over whatever account is configured for unconstrained delegation. So that could be either a machine account, so essentially we gain a local admin on the target machine, or if it's a user account, we can simply have the domain credentials of this user account. And with that, we can then go on with the attack. From the modus operandi, there's basically two ways on how the abuse can take place. Either we are lucky and the service that is, or the system that is configured for unconstrained delegation already has some TGTs of interesting users cached. So that means when we compromise the server, the ticket cache already contains some TGTs of users that have connected previously, and this cache is regularly cleared up, of course. And if we are not lucky, we need to somehow either wait for an interesting user to connect or help this along a bit and coerce a user or a machine that we are interested in to connect to our service. And then as a result, the TGT copy will be made available, and we can then abuse that. Now, how can we actually look at those tickets once we have control over a host? Here I'm currently on WS1, which we know is configured for unconstrained delegation, and I have Mimikatz brought along, and you can see we are also in an administrative share, so we have local admin rights. I'm going to start Mimikatz and just configure a log output file, and then with we increase the privileges to debug level, or we enable the debug privilege, and then with the secure LSA tickets command, we can essentially dump out all the tickets that are currently stored within the ticket cache of this system. Now here in my machine, this will take quite a while since there has been lots of user activity going on. We see lots and lots of tickets being dumped at the moment. This always depends on the activity level of the machine, of course. And once this is done, we can quit out of Mimikatz and have a quick look at the output that we configured. Let's jump to one specific user that we would like to, because here it's quite a mess to orient yourself here. Let's look for one user, in our case ffast, and with an entry for this user, we see that we essentially have two ticket groups. One is for service tickets, so tickets issued by this ticket granting service. We can see, for example, LDAP for DC1, and then the second group is the ticket granting ticket. So this is the KRB TGT ticket for ffast. And then the same thing applies to other users as well. With the command that we have issued, Mimikatz will also dump those tickets into a Kirby format. So here we have all the tickets that we've seen in the log output previously stored as individual files that we can then copy over to other machines and use it from there. Now, another way to get to those tickets is, for example, the tool Rubius. Again, I'm on WS1 with administrative privileges, and with Rubius, we can first of all use the klist command to just check what kind of tickets are available, and we see essentially the same thing as before. For example, a KRB TGT ticket or a ticket granting ticket for ffast, LDAP ticket, CIFS ticket, and so on. And then when we actually want to get to the content of the ticket, we can use the dump command, which will then flush out all the actual contents of the ticket in a base64 form that we can copy and use from other systems. So here, again, various tickets available for both service tickets and ticket granting tickets for the respective users. Now, we can also filter for specific users. So we can say, I'm just interested in the tickets of ffast for now, which will then only limit the output to all tickets that apply to the current user. So again, we see essentially the same output as before, but now targeted towards a specific user. Lastly, when we now talk about we're interested in new tickets that are incoming, we can use the monitor feature of Rubius with a certain interval. I have configured it now for 10 seconds. So if we look at the starting output, Rubius will now look for new TGT, specifically TGTs only, no service ticket, every 10 seconds, and list those in the output. We can quickly simulate now what happens if a user connects to this system. I'm simply going to issue a dir command on WS1. You can see that we get an error that access denied, but that doesn't really matter for our demonstration since Kerberos flow still takes place in the backend. So the permission does not really matter as long as the Kerberos flow takes place. And we can see that indeed Rubius has found a new TGT of our user Trevor Massey. And this base64 blob is then actually the ticket, the TGT of Trevor Massey. Now, a few details on how you might be able to trigger those connections and get users to connect to your system that is configured for unconstrained delegation, because in most cases you maybe don't have the time to simply wait until somebody interesting connects. So if you don't find any useful tickets to begin with, you might want to target specific users or machine accounts that are configured with high privileges within the domain to connect to the system that you compromised. For that purpose, we as an attacker need to coerce the target to connect to our services, and there are various ways to achieve this. Essentially, this is the same attack scenario as NTLM relaying, so similar options apply. So we can use the responder tool to poison ARP requests, or we can attempt to do DNS poisoning. We may set up a rogue DHCP server. We can attempt to phish users with links to connect to our system, or we can use various well-known mechanisms like the PrinterBug or Petit Potam and similar features to trigger systems or core systems to connect back to our machine. One specific example I would like to demonstrate here is the PrinterBug. The PrinterBug is essentially a feature in the Microsoft Print System Remote Protocol, which and the protocol itself is part of the print spooler service. Now, if this print spooler service is exposed on the network, typically it's used to handle print jobs and tasks related to that. It can also be abused, or this PrinterBug becomes abusable. If you as an attacker make an RPC call to this service, a specific one, you can basically force this service or the target you're connecting to make another connection to any host of your choosing. So the connection that then comes from that is performed via SMB, either using NTLM or Kerberos, depending on how you specify the connection. And it will also be authenticated, so it will carry authentication material from the system that you targeted. What you require to do this as an attacker is simply a valid domain account, so no specific privileges required, and of course network connectivity to the systems involved. Now, this specifically has been shown quite a few times that the PrinterBug in combination with unconstrained delegation can be used to quite easily gain domain admin privileges. And this is an attack I would now like to quickly demonstrate to you. So what we do is we as an attacker have already control over a system configured for unconstrained delegation, and we then abuse the PrinterBug to trigger a domain controller to connect back to our target machine. Since the target machine is configured for unconstrained delegation, a copy of the domain controller's TGT will be sent to us, and since domain controllers are by default configured with DC sync permissions, so they can replicate essentially all the data stored on a domain controller between each other, including the secrets, so the key material and password hashes of users. We can then abuse this TGT to essentially perform a DC sync attack and become any other user within the domain. If we look at this in a graphical overview, We start with the following picture. So we as an attacker, we are interested in the system that is configured for unconstrained delegation, for example, a web server. And the first thing that we need to do is we have to somehow compromise the system. So we need to gain local admin permissions on it. However that happens doesn't really matter for this demo. It's simply a prerequisite. Once we have this local admin access here, we can essentially, as seen before, start the Rubios in the monitoring mode and wait for incoming tickets. If we are unlucky and no interesting ticket is now in the cache, we can help our luck a bit and basically force the domain controller to connect to the web server. For this, we abuse this PrinterBug that we have discussed previously. So we resend a specific request to the print spooler service running on the domain controller. And as a result of that, the domain controller will then issue a connection to the web server. If this connection is authenticated via Kerberos, this essentially depends on whether you specify the IP address or the domain name, the fully qualified domain name of the system. Remember, Kerberos typically only works with domain names. The authentication sent from the domain controller will include a copy of the domain controller's TGT. And since we are local admin on the system, we will be able to extract the TGT from the ticket cache of the system. And with that ticket, we then can essentially go back to the domain controller, either the same one or a different one, present a TGT, and perform a DC sync attack. Now we can look how this plays out in real life. Currently I'm on WS1, so this is the machine configured for unconstrained delegation. And as before, I'll start Rubios in the monitoring mode to watch for tickets, new incoming tickets. Now we already have some tickets in the cache. For now, we are going to ignore them since those are not the tickets that we are interested in privilege-wise. So we just leave that running and help ourselves to a specific ticket. From our Windows client, so this is a regular domain machine, I'm going to use, in our case, spool sample, which is simply a proof of concept implementation to trigger the PrinterBug. So you can find that on GitHub, and there are other tools like that available as well. And with spool sample, I simply need to specify which system I would like to connect to where. So where do I connect to the spool server? This is on the DC. And what's the target? This is WS1. So we'll check again for the tickets. We currently have nothing new. And now I issue this connection. So the DC is now trying to connect to WS1. And if this really works, we should now in Rubios see that we indeed have a new ticket. And this is really the case. We can see the ticket is for DC $1, so the machine account of the domain controller. And this in the output, then we will now find the actual TGT of the domain controller. If we go now to the abuse step of this TGT, we can simply use Rubios because we can pass a ticket in its base64 encoded format to it. So I'll just copy over the ticket that we stole from WS1. And if I now look into my logon session, I can see that I really have the KRB TGT, so the ticket grounding ticket of the DC1 in my logon session configured now. With that, I can then use another tool, for example, Mimikatz, that can perform DC sync, and it will simply use the ticket that is now in my logon session to connect to the domain controller and dump the credentials. So I'll just call the LSA dump DC sync module on the domain, specifically on a specific user called lab admin, and we can see that this works perfectly fine. So with the ticket that we have stolen, we are able to receive or retrieve the key credentials and telm hash and so on of this user. Now onto the recommendations. What should you think about when you want to use unconstrained delegation or when unconstrained delegation is in use currently in your domain? First of all, as we've learned now, the unconstrained delegation is essentially the most insecure form of delegation. So whenever you configure this on an account, this account automatically becomes a very high value target for attackers. The best recommendation now in this case is essentially to not use unconstrained delegation and replace it by one of the other delegation mechanisms that we are going to talk about in the upcoming parts of the video series. However, if you have to use it for some reason, you should consider the following points. First, and this is basically directly taken from the Microsoft documentation, you should protect the affected accounts or systems as strongly as possible, as strongly as you will protect your domain controllers. That could mean hardening applied to it, network separations, and so on and so forth. So the chances or the risk of an attacker compromising this system is as small as possible. Then, if you cannot entirely prevent the compromise of the system, you might think about addressing the consequences. So if an attacker compromises a system configured for unconstrained delegation, you might at least use the protected users group to protect your high privileged accounts, or you can also mark them as sensitive so they cannot be used in the delegation process. And then in general, of course, reduce the permissions available to your accounts. So if every second user in your domain has domain admin privileges or other high level privileges applied to it, then of course it makes the abuse much easier for attacker because every second user is a high value target then. Then it also helps to disable all those kinds of coercion and the remote connection trigger mechanisms like the print spooler and so on. However, there are always new ones discovered on almost a weekly or monthly basis. So this is quite a difficult thing to do, but still in terms of system hardening and network separation, it will be a good idea to restrict the availability of these services. So it's less likely that an attacker is able to coerce your systems into connecting to other accounts. And then, of course, you can also implement monitoring measures, specifically targeting your high value accounts and the systems that are configured for delegation. Now that we have learned on how the unconstrained delegation mechanism works, there are a few more details I would like to go into, specifically regarding this mechanism where the TGT of the user that connects to a system for unconstrained that is configured for unconstrained delegation is copied. If we quickly recap this, we have learned that when unconstrained delegation is enabled, the delegating service, so the service that has delegation rights configured, will eventually receive a copy of the user's TGT. The KDC, so the ticket granting server, essentially will indicate to the user or to the client that the target it wants to talk to is configured for unconstrained delegation with this flag. And automatically, when this is indicated, your Kerberos client will request a copy of your TGT, and the copy is then eventually forwarded to the target service. So this is all happening automatically. You cannot really prevent that. And then the ticket is transferred to the target service, specifically in the AP rec part of the Kerberos authentication flow. We can quickly look at that in Wireshark. So I'm on the domain, on a regular domain computer. I have Kerberos set up in Wireshark, and first I'm going to purge my current tickets, and then I'm going to issue a request to WS1 to some share. Whether or not this exists doesn't really matter again, because it's essentially just a mechanism to trigger the connection. And now if we look at Wireshark, we see the familiar things. So the first 4 requests we already know. This is simply requesting a TGT without pre-authentication and then with pre-authentication. So the first actual request we're interested in is the TGS rec, where we ask for a service ticket for CIFS on WS1. So this is happening when we type the dir command. And in the response, we will see that the ticket granting server sends us back, among other things, this indication OK as delegate. So the flag is set, which means that WS1 that we would like to access is configured for unconstrained delegation. Automatically after that, as mentioned before, our client will then issue a second request, again TGS rec, to fetch the copy of its TGT. So we see we request a ticket for the service KRB TGT on our domain. This is the same thing as it's for a TGT. And in the response, we then, the ticket that we get back from that is really the issue to the KRB TGT account within our domain. So it is encrypted with the key material of the KRB TGT account. And then along with that, we also have the corresponding session key that is used for this ticket. The forwarding mechanism then lastly takes place in the AP rec. Now remember again here in our case, the AP rec is wrapped into the SMB protocol. So the SMB protocol uses Kerberos underneath to authenticate. So we have to drill down a bit into the data structure to arrive at the AP rec part of the message, and we can see that first we, as usual, we forward our service ticket for CIFS on WS1, and then we also send the authenticator. Now normally the authenticator would only contain username and timestamp in an encrypted form. Here we have a bit more information now included because we forward this the copy of our TGT, and this is actually part of the checksum data structure, and within that we have the KRB cred data structure. Now in KRB cred we find the actual ticket and the session key, the encrypted session key that belongs to the ticket. So within the ticket we can see that this is our TGT, so it is issued to the KRB TGT account. And then in the encrypted part, we find the session key that is associated with the survey with the TGT that is forwarded. Now you might ask yourself, why is it a copy that is used and not simply the exact same TGT that we already have as a user? Theoretically, it would be possible to simply forward our original TGT to the delegation service. However, if you remember or think back to the basic mechanisms of Kerberos, we know that a ticket is always only usable with a corresponding session key. The session key, when it is transferred, is always bound to a specific client or recipient via encryption. So it is encrypted with a specific secret. And if we share the same thing with another machine, with another system, this would essentially violate the separation principle. What's been done now in reality is that as we've learned, a copy of the TGT is created, a new session key along with that as well, and this session key is then intended for the target service. So this makes it so that the copy of the TGT is then essentially traceable, and its usage can be audited, and you can figure out whether an action was done via the user TGT or via a TGT that was issued to a delegation service. To quickly show you that there are really different session keys associated with it, again, back on my machine, I will, as before, issue a request to WS1. This will fail. Again, doesn't matter, but as a result, we get our tickets. And if we use klist, we can see that we now have two KRB TGTs, or ticket granting tickets. One is the so-called primary, and the other is the delegation, so the copy of it. Both are within our logon session. And if we now use mimikets from an administrative prompt, we can flush out all the details of those tickets and look at the actual session keys configured for those respective tickets. So first I'm going to dump all the tickets, and then from here we can inspect the output and look for our user to see those tickets. So in the ticket granting ticket output in group 2 specifically, we can see that we have those two TGTs, and they should now line up with what we've seen in the klist command before. We have one of those that is marked as forwarded, so this is the delegation ticket, and we can see that in this output as well. And the other TGT is or you can see the session key as well associated with it. And the second TGT doesn't have the forwarded flag set, only the forwardable. So this will be the entry number 1 in our output, which is the primary TGT. And you can see the session key obviously differs between those two. So they are really separate and not identical copies. Now, a word on how those session keys are actually accessible. You've seen before that I used Mimikatz from an administrative command prompt to actually dump the session keys. So this maybe requires a bit more specification. So what we've seen is that we know that session keys are always associated with either a ticket granting ticket or a service ticket. Session keys associated with the TGT are used to communicate with the KDC. The whole communication with the KDC, this first step of the Kerberos authentication flow, is handled by the authorization system of Windows, so the LSAS, and the key material or the session keys in its raw or in their raw form are not accessible to a regular user without local admin privileges. So there's no way we can dump them. However, session keys associated with the service tickets, they are used to communicate with a target service. And this is typically done from a user application. So you start an application and this application then wants to communicate with a service. So the session keys and the associated key material is handled or exposed in the security context of the application that uses the service ticket. And with that, it also means that we as a user are able to access the session keys and dump them essentially without requiring local admin rights. You still cannot dump service ticket session keys from other users on your machine. For that, you would again need local admin rights and only within your own process. Otherwise, you would require debug privileges to access the memory of other processes, of course. So with this information about the accessibility of different session keys in mind, let's look again at the whole flow where we request a TGT copy in the context of unconstrained delegation. And let's look specifically at how the keys are related to one another and what that results in the end. So the situation that we start from is that we have a user on the left side, Alice. She already has some keys available, specifically her own long-term key derived from her password and a session key to communicate between herself and the TGS. This is part or a result of the ASREC and ASREP exchange, so just getting a TGT. And on the TGS itself, we have its own long-term secret as well as the session key between Alice and the TGS. And on the right side, we have a resource that we would like to access with its own long-term secret as well. And this resource specifically is configured for unconstrained delegation. Now, the flow itself that we are going to look at are 5 specific messages. We start with the actual ticket request or service ticket request for the target. Then we have the TGT copy request and response, and eventually the AP rec to the actual target. So first, we start with the service ticket request for FS1. There's nothing peculiar about this request or worth pointing out. This is simply a request for the resource that we would like to access. The TGS will subsequently generate a new session key. The session key is intended to secure the communication between Alice and FS1, and it will also create a service ticket for the target. This will be returned in the TGS rep, so we have the service ticket which contains the session key, and as well as the session key again separately encrypted with the previously established key between Alice and the TGS. In this message as well, there will be the OK to delegate flag, as we've learned before, since the target that we would like to access is configured for unconstrained delegation. Now the client will extract the session key from this message, and since this session key is associated with a service ticket, it will be accessible to us as a user. That means we can extract it programmatically and use it ourselves. Then, since the OKS delegate flag was specified, our client will request a copy of its TGT. So it will send another TGS rec. That will be request number 3 in the Wireshark record. And this request, again, nothing special about that. And when it's parsed by the TGS will create a new session key, which is intended for the communication between FS1 and the KDC. Now this might look a bit confusing in the beginning, but again, remember that this session key is intended to be used with the copy of the TGT, and the copy of the TGT will be used by FS1 to request new tickets from the KDC or the TGS, and therefore it will also need an according session key. Then with the TGT copy as well, this will be sent back to our client. So we have another message, a TGS rep, containing the copy of the TGT with its session key and the session key belonging to that TGT, again encrypted with the previously established key. At this point, the client will extract this session key, and since this session key is also associated with a TGT, it will not be accessible to us, so we cannot get access to that directly. Finally, our client will then send the AP rec to the actual target. In the AP rec, as per specifications of Microsoft, we first send the service ticket. This is simply this data that we received up here, and then the authenticator. We've seen that before in the intro to Kerberos. However, in this case, the authenticator has been extended because we have requested a copy of our TGT. This copy will be included within the authenticator. So this is just what we got back here. And then the session key associated with this TGT copy will also be included next to the TGT. And as you can see, both the authenticator as well as the session key that is associated with the TGT copy are encrypted using a key that is accessible to us as a user. That means at that point in time, this whole data structure here can be decrypted, completely decrypted, well, with the exception of the TGT, of course, which is encrypted with the long-term key of the KDC. But we get access to all of this information here, since we have the respective encryption key is accessible to us as well. That means at this point we learn the session key associated with the TGT, and we get the TGT itself in its encrypted form, but that's all we need. So at this point, we have both a TGT and an associated session key, which is available, accessible to us as a user. Now let's trace this protocol flow with Wireshark. For this, I'm going to again issue a request to WS1, which is configured for unconstrained delegation. This will fail as we've seen before, but it doesn't really matter because it will still trigger the Kerberos flow. So the structure-wise, we see the usual, the AS rec and rep, so the TGT request, then the service ticket request, followed by the copy, TGT copy request, and then eventually the AP rec within the SMB2 protocol, which forwards our ticket. Now, if we dig down into the actual part where the copy is in the authenticator, we will eventually find the KRB cred structure, which contains the actual copy of our TGT. So we can see for the KRB TGT and the session key, the encrypted session key. Now, this session key with a value 047B, we can see how it was actually encrypted because Wireshark displays that information to us, and it tells us that the key eventually came from frame 1514. And if we go back to that, we can see that this was the response to our actual service ticket request. So whenever we first fetched the service ticket for CIFS on WS1 in the response, we then get the service ticket itself along with a session key that is intended to be used in combination with that service ticket, and the same session key A3CB56 here is then used to eventually encrypt the session key that belongs to the copy of our TGT, as we can see here as well. So let's again summarize what the main benefit of this whole mechanism that we just discussed is from the viewpoint of an attacker. We have learned that it essentially enables us to request a copy of a user's TGT, and this is quite valuable to attackers, since if you imagine the following situation, that you as an attacker can run code in the user's context, so that might be that you have a malware implant running on the user's machine, but you don't know the user's Windows password, so you cannot impersonate the user by simply running code from any other system and providing the password. However, what we can do with being able to run code in the user's context is to request tickets. So we can issue a request for a TGT, or we can issue a request for a service ticket. And what we would like to achieve is to actually extract a user's TGT to use it from maybe another system like a Kali Linux. However, this requires local admin privileges if we talk about the primary TGT of a user, since this is only kept in the Alsace memory, Alsace process memory. Now, instead of trying to work around that, we can essentially abuse the mechanism that we just learned about on the previous slides. So from the user session, what we do is we request a service ticket for any given service in our domain that is configured for unconstrained delegation. And here we can take advantage of the fact that the domain controller is always enabled for unconstrained delegation by default. That means if we simply request a service ticket for any service on the domain controller, for example, CIFS, LDAP will work as well, we trigger the TGT copy mechanism automatically. So when the KDC receives our request for the CIFS service on the DC, it will see that the DC supports delegation, and then this will trigger the TGT copy mechanism. And with, as we've seen before, within this mechanism, we have the possibility to actually extract the TGT as well as the associated session key, and then use that or have it available in a usable form, so we can copy it over to other systems and use it from there. The attack feature that we just discussed on the previous slide is also built into several tools. For example, in Rubius, this is called TGT Deleg. And what we can do with that is exactly what we just talked about. We can extract or acquire a usable TGT from within a user session. That means the TGT and the associated session key without having local admin privileges. And how it works, it's essentially a repetition of the previous slide. So Rubius will by default ask for a service ticket on for CIFS on the domain controller. Now this is the default configuration. You can override that if you have another system that is configured for unconstrained delegation. And then when this request is parsed by the DC, it will obviously check if the target, so the DC itself, is configured for unconstrained delegation, which is the case. Subsequently, the client will request a copy of the TGT, and then to finally access the actual service, so the client will prepare the AP rec data structure in its memory, and inside the AP rec, as we've learned before, within the authenticator, we have the TGT copy as well as the session key. And Rubius simply then extracts this information from the data structure. It will load the according session key, which was used to encrypt the authenticator. It will decrypt the authenticator, get the TGT copy and the session key of the TGT out from it, and then presents this information to us in a format that we can then use on other systems. By the way, the actual AP rec to the target is then not sent by Rubius. We will see that on the next slide when we monitor this with Wireshark. So Rubius simply fakes let's say a delegation attempt and doesn't actually follow it through to the end. It simply drops the AP rec once it has acquired the required data. We can look at that again in Wireshark. So on the right side, I first clear my ticket cache and then issue the TGT deleg command in Rubius. As a result, we get quite a lot of requests. Let's stop Wireshark and go through them step by step. We can see what Rubius actually does. It tries to access the CIFS on the domain controller by default. So it initializes the whole Kerberos system and makes a request for CIFS on the DC1. And as a result, it will then it will trigger this copy mechanism. And once the AP rec part has been prepared and is essentially in the memory of our process, Rubius will then access it and extract the session key and the authenticator from it and decrypt all the required data and then dump the actual TGT along with the session key so we can copy it to another system and use it from there. Let's look at Wireshark. So what we can, again, ignore the first 4 requests. This is simply requesting a TGT. And then the follow-up request is concerning LDAP, so we can skip over those as well. They are not related to what we are doing. The first one that is actually relevant is the service ticket request for CIFS on DC1, as we can see in the output of Rubius. In the response, we get, as expected, our service ticket for CIFS on DC1, along with the encrypted session key that we can use to then communicate to the target service. And again, the flag is also set OK as delegate, so we now have to get a copy. And this is the next request that happens. So our client requests a copy of the TGT, so it makes a request for KB TGT on DC1, and as a result, we get back the actual copy along with the encrypted session key. Now this we can at this point not extract yet since it's not accessible to us, but we can see the session key here in Wireshark. Now the AP rec is missing here, and again this is because Rubius simply waits for the AP rec data structure to be constructed and then dumps the actual request. So it will simply parse the memory to extract the data, but it will not send the actual AP request. Now to see that everything actually lines up with what we see in Wireshark, let's quickly inspect the ticket. We'll switch over to our Kali system and paste the base64 encoded content into a file. Next we decode it, so it's in the Kirby format that is then processable with other in-packet tools. And then we use the ticket converter command to convert the Kirby ticket to a Ccache ticket. And from that step, we can then use the in-packet describe ticket command to look at the contents. And now we see that this is the actual KRB TGT ticket, so a ticket granting ticket for Trevor Massey, and we also can see that it contains the associated session key. So again, session key E8F706, and if you go back to Wireshark, we can see that it is exactly the same session key as depicted here. So this actually lines up, and we were able to extract the usable service ticket, ticket granting ticket. With this, we have reached the end of part 4 of our Kerberos deep dive series. If you've got any questions or remarks, please leave them in the comments. Thanks for watching.